All right, hello everyone, welcome back. So this is a part 2 of a talk I previously did. So I'm going to do a quick recap of what we covered last time, just in case some people missed it. Quick recap. So last time around I talked about, the steps to design a programming language, and designing a programming language ends up being about coming up with a non-ambiguous specification of program behavior. And program behavior I defined as some sort of machine behavior, where a machine is some sort of automata that takes steps in a very mechanical manner. So, the steps I discussed were you have to come up with some basic constructs in your language, and you have to describe basic operations for those on those basic constructs. And then you have to describe some way of composing basic operations together. And you also had to describe some notion of an answer, some notion of when you're done computing. So you know that, this is the answer that you were trying to compute. And I described the language. Here's that entire language in one slide, except for the machine steps. So the language had expressions, variables, field reads on variables, function calls on variables, and some inputs, and some literal bindings and some let bindings. And we described our basic constructs as being objects or functions. And we described an abstract machine which had some evaluation context and a heap sigma. And we described an answer is if you're done computing in terms of the evaluation context, and you have just a variable or some pointer to some object in the heap, that's an answer. So here are the operations I described last time around. We don't have to go through all of them, but the only one that's important for this talk is the first one, where if you do field read, then you look that object up in the heap and then read that field. That's what happens when you do field. So now I can talk about this talk. My phone on silent. Types. This talk is going to be about type safety, and if I asked most of you what type safety is, you will probably answer something along the lines of, not doing the wrong thing. You'll probably describe things along the lines of, type safety is about not calling the wrong method on an object, or not trying to read the wrong field, or trying to add two objects together where there's no notion of adding those objects together or defining your language. So keep all of this in mind. What is type safety as we're going through this talk, because we're going to formally define what type safety is later in the talk, but keep this in mind that, hey, our purpose is to kind of reduce these wrong behaviors in our programs. So again, kind of what are types? There are many different things you have to think about. So you have to think about types, and you have to know what a type system is, and then kind of reason about type safety as well. So these are all related concepts, but you can kind of define types first, and then type systems second, and then describe type safety. And that's how I'm going to approach it. So I'm going to say that a type of an expression E is some representation of the operations allowed on E. That's what a type is. This is a very operational view of types. There are other views of types, but this is the philosophy I'm taking for this talk. But types represent some notion of the operations that are allowed. So, for example, we're all familiar with the type int in most languages, and the type int represents these sort of operations where the type int represents that you can add this thing to another int, and you can also pass it to functions which expects integers. So these are the kind of operations we're trying to represent with types. So kind of going back to the language I defined last time around, we describe a call by reference language. So we're going to describe types related to that. So in our language, expressions all compute down to a reference to some basic construct, some pointer to some basic construct. So types need to represent operations on reference to these basic constructs. So that's what we're going to do next. So for our language, we're going to describe two kinds of types. So the first type is an object type, which will describe all of the fields and the types of things that those fields contain. And we're going to have function types. This is the function types, where input types are t1 to tn, and the output type is t. And this closely mirrors what basic constructs we had. Our basic constructs were objects and functions, so we have to describe types a lot on these basic constructs and basic functions. Let's go and describe the operational view that we have based on these types. So if you have any type t, we're allowed to pass it to a function. If you have any reference or expression of type t, we can pass it to a function expecting t as an input, the input type t as an input. That's an operational view of what any type means. If you have an object type, then that means with a field A containing something of type t, that means then we can read the field A to get a reference of type t. And if you have a function type, then calling the function with inputs of types t1 to tn returns something of type t. So those are the operational views that we need for the language we described earlier. So that's types. We've described all the types we need, but we haven't really described how to give types to expressions, and that's where type systems come in. So type systems, a type system is just a collection of rules for giving types to expressions. For now, we're not going to worry about whether we're giving sensible types to expressions. In most realistic languages, you fudge this sensibility a little bit. So for example, in Java, sometimes you give slightly broader types to arrays than you should. There's some unsoundness that creeps in by having in some sense, wrong rules, but we're not going to be worrying about whether these rules make sense for now. But a type system is just a collection of rules, that's all. And to design a type system, we need to go through these 4 steps. And they follow the design steps earlier, in some sense. So we've already described types for our basic constructs, so we're kind of done with the first step. We described what types are. And then we have to go and give types to our basic constructs, our basic operations, and our composition operations. And to do this, we need some technical infrastructure. So we need something called a typing context, and we use the notation gamma for these. This is standard notation from the literature. A typing context is a set of assumptions about free variables, and it looks like this. So a gamma would look something along the lines of this, where you have an expression, and you assume you have a variable x1, and you assume x1 has type t1, and so on and so forth, all the way to some finite number. And you can perform lookups on these assumptions. So if I want to know what type I assumed x1 to be in gamma, then I can look it up. And using typing context, we give types to program fragments, not just whole programs. We use this notation for typing program fragments, where we say that under the assumptions gamma, the expression E has type T. Okay. Another part of the technical infrastructure is we need to give types to variables. So this is a typing rule. There's a bar. It says that, and the way we read this is if, when we look up the type of x in gamma and we get t, then X has the type T. So this is if, and then this is a consequence. If this holds, then this holds. So that's how we type variables. And then we can start typing our basic constructs. So if x1 has type t1, x2 has type t2, so on and so forth, then the object a1 assigned to x1, a2 assigned to x2, and so on and so forth, has the object type a1 of type t1, a2 of type t2, so on and so forth. This closely mirrors the object itself, so that's the type of the object. Now let's type functions. The way we type functions is if gamma, together with the additional assumptions x1 to xn having types t1 to tn, types the function body e with type t, then the function which takes x1 to xn and tries to compute e has the type t1 outputs t. The t1 to tn outputs t. This is the function type, so that's the type of this function. So this is an unnamed function type. So in C and other languages, you might be more familiar with having the type, like the output type appearing first, but it's just different notation for the same concept. And this function is unnamed rather than having named. So in like forward declarations in C and so forth, you put the T first as the output type and then name the function and then give the input types. So those are types for our basic constructs. We had objects and functions and we described types for them. So we're done with the second step. We can now move on to giving types for our basic operations. So our first basic operation was a field read. So if X has the object type which contains the field A1 of type T1, then X.A1 has type T1. So this read would output something of type T. Similarly, we have function calls as one of the basic operations. So we need to describe how we type function calls. So if f has the type this function type, and x1 to xn are correct input types, then calling that function would produce the right output. So that's basic operations. Now we need to describe types for compositional operations. So we had two compositional operations, literal bindings and lead bindings. They look very similar and we type them in a very similar way. So if we can type this object or a function, which I use the notation h for, has type th, and gamma with the additional assumption x has type th, types e with the type t, then this literal binding has type t. So let x equals h in e has type t. Similarly with lead bindings, rather than just literal bindings, we're just replacing the h with e1, and instead of th we have t1. So let x equals e1 in e2 has type t. And that's it. We've described the type system for our language. Is this type system sensible or not? We don't know yet. But we're done describing the type system for our language. We have some notion of this program is well typed or this expression is well typed. But to describe whether or not this type system is sensible, I need to describe what type safety is. You have a
What do
question?
you mean by sensible?
are we giving wrong types to expressions, or are we allowing more types, more operations on some expression than we should? That's what I mean. So that's where type safety comes in. Type safety is a property of type systems. We already described what a type system is. So type system can have this property or not. And we say that a language with a type system is type safe if all well-typed programs in the language are guaranteed to either return an answer or run forever without crashing. So you either return an answer or you go into some sort of infinite loop. And you never kind of crash while you're in this loop in some sense. Any questions?
What is the language returning an answer?
So programs are returning an answer. Programs compute down to an answer. That's
And this answer being, is it type safe or not, or you mean that it's actually computing something?
It computes something without getting stuck while making transitions in the abstract machine. And I described for our language, an answer is some pointer pointing to.
How do we know if it's running forever? How do we know it's not internally crashing?
That's what it means to be type safe, that it won't. So if you have a good type system, you're guaranteed that it won't crash.
So what do you mean by crash?
By crash, I mean, you don't get stuck while making steps in your abstract machine. So you're not doing weird things like trying to read a field on a function. Right? Like that's not a sensible operation. You're not making any of these nonsensical operations. That's what my next slide is kind of trying to say. That hey, we're not trying to perform bad operations anywhere in any of our type check programs. So we're not going to try and do field selections on functions. We're not going to try and do field selections on wrong fields. So if the field A doesn't even exist on this object, we're not going to try and read A. We're not going to try and call an object. Like we can only call functions. We're also not going to do weird things like calling functions with the wrong number of arguments and so on and so forth. These are operations that our abstract machine does not define, and so.
So a crash here means one of those operations, because the
Yeah.
program can crash for other reasons, right?
Not in our description of the machine and
So
language.
this is an abstract definition of, or a theoretical definition
Yeah.
of, okay.
Yeah, well, it's described with respect to the abstract machine rather than implementation. So,
I mean, if you're thinking about it as like an add function, but it's doing subtraction, technically that's a
But
bug
if
or
it
a crash. But
if it crashes for other reasons.
like running out of memory, that's
Yeah,
an
or an
implementation
operator
defined
exception
thing.
or- okay, so that's what I'm saying, like a crash is defined as one of those operations, not any crash.
Yeah,
so if
yeah.
you're running forever, you're running, but you're not running into any of these
Yeah, you're gonna
bad operations.
even if you run forever, you never run into any of these cases. And the way we show that some type system is type safe, there are again steps. This entire series of talks has been about describing steps to do these things. So to show type safety, we need a type system not only for our language, but for our entire abstract machine. So we need to expand what we give types to our entire abstract machine. And then we follow these steps from this paper in 1994 by Wright and Eliason. It's a very famous paper where they describe type safety, showing type safety of type systems as being proving these two lemmas called the progress lemma and the preservation lemma. Those are described in the next slide. So progress says that a well-typed abstract machine is either an answer, so we're done computing, or can take a step. And preservation says that whenever a well-typed abstract machine takes a step, you end up with another well-typed abstract machine. So taking a step does not mess with types in any way, and taking a step does not allow you to do more operations than what is allowed by the type system. So to give a type store an entire abstract machine, we need to give type store heap and our evaluation context. So the way we give type to a heap is we say it corresponds to some typing context. So the way we say it is a heap corresponds to some typing context gamma if the heap and the typing context have the same domain. So if X has some type T in gamma, then X is also bound to some object or function in our heap sigma, and vice versa. So if you have some object or function in sigma, it will have a type according to gamma. So they have the same domain, and gamma also gives the right types to things. So if some variable X is bound to some object or function in sigma, so H, then gamma will give H the right types. So H will have the type that's bound in gamma. So all of that saying is gamma does not make wrong assumptions about pointers to heap items. So that's giving a type to heap. So we kind of think of the type of the heap as being this typing context. And next we give types to evaluation context. So the empty evaluation context has this type T arrow T. And what these kind of types mean is if the focus of execution in your abstract machine has the first type, then once you're done computing, you'll end up with something of type T. So that's a little more clear in the next one, next typing rule. So what this is saying is if you have this evaluation context, let X equals some hole in your evaluation context and E together with some other things in your evaluation context. This will have type T1 to T3 if gamma with an additional assumption that X is type T1 gives E the type T2, and this evaluation context E was already typed as taking T2s to T3s. So all that's happening is if we fill this hole in with something of type T1, then this whole thing will have type T3. That's all we're saying. Questions? Yeah.
Isn't this typing rule kind of assuming what you're trying to prove with the preservation lemma? Doesn't this say that types will be preserved when you evaluate this let expression or go through this evaluation context?
Yes and no, but all we're kind of caring about with these is we're not going to break well-typedness in any way. We're not going to introduce any weird things, right? If that makes sense. Maybe you can repeat your question.
Okay, yeah. So, like when we're trying to prove type preservation, like what we're trying to say is that for every well-typed program that has like, if the entire expression we're evaluating has type T, then when the program finishes, whatever answer we end up with will be typed with T, right? So isn't this typing rule kind of saying that if you
kind of, yeah. Well, it kind of needs to say that anyway. But we never say anything along the lines of we finished every compute. We don't say anything around the lines of like, oh, we will eventually finish computing or anything like that. So we can keep adding things to our abstract machine, into our evaluation context while executing, and never actually compute down. But we'll still end up with well-typed abstract machines. That's what I'm trying to do. So we've given types to our, like the components of our abstract machine, So now we can give a type to our entire abstract machine. So our abstract machine with the focus of execution E, evaluation context capital E, and sigma has the type T if sigma corresponds to some gamma, typing context gamma, and gamma gives the right types to the focus of execution and evaluation context. So E has the type T1 to T, and small e has the type T. Then this entire abstract machine has the type T. So that's the first step of showing type safety. We describe the type system for our entire abstract machine. And then we go and follow this right initialize and steps of showing progress and preservation. I'm not going to show progress and preservation because that would take too long. But I will kind of give an indication of what kind of things you need to show. One caveat is that since our language is so simple, it has no subtyping, no fancy features, some of these lemmas are way easier in this language than in a more realistic language. So keep that in mind. I'm going to describe a lemma called the canonical forms lemma. It's very easy in this setting. It's much harder in other languages. So for showing progress of basic operations, you end up needing to show this canonical forms lemma, which essentially says that types indicate the shape of items in the heap. So if gamma corresponds to, if sigma corresponds to some gamma, typing context gamma, and gamma says x, which is the pointer in this case, has some object type, then the heap will actually bind some object type. And we'll also know that that object will have the field A, and this A will contain some pointer x1, and x1 will also have the right type. So you need to show these kind of lemmas, and so this was for objects. You can show a very similar thing for functions. I'm not going to describe that other than saying that, hey, if you have a function type, then sigma binds f to a function. And in our language, this is very easy because heap correspondence was so nice. If you have subtyping, heap correspondence becomes less nice, and these things become harder to prove. So just keep that in mind that, hey, this is much easier in our language than you'd have in more realistic languages. So that's canonical forms. I'm going to show how progress is proved for field reads. So if you have a field read operation, and this field read is done in a well-typed abstract machine, then you'll have these conditions from the well-typedness of this abstract machine. And for field reads, a field read will succeed if you have that the heap binds to the right kind of thing. So you're doing an x1.a, and it succeeds and returns x2 if x1 is bound to an object containing x2 in the field A. And the way you prove it is you know that you have x.a has type T1. So this can only come from x having this type. And then you apply the canonical forms lemma to show that it will contain some x1. X will be bound to some object, and it'll contain a field A bound to some x1. So the field read will succeed. It won't fail. And over here, showing that X is bound to the right kind of thing, to show that you can progress and not fail, is where the canonical functionality comes in.
Isn't that like an estimation of the type, or is it actually a machine operation? I mean, is that canonical form that you get at the end, is that an estimation, a computation of values, or matching values?
Canonical forms is almost a property that holds of a well-typed abstract machine. That so it's saying that X in this abstract machine, X will have the right kind of shape, right?
Yep.
Yep.
And the previous one means that there is an x1 for which A is going to be.
Yeah.
It's
It's saying that we
right.
can read X1 from the field A in X. And that's it. If we actually finished progress and preservation, we would have finished showing that our language is type safe. But we didn't do that because we only showed it for one subcase of a subcase. But we could finish progress and preservation for this language. It's not that hard. It gets harder when you have a much more complicated language. And that ends my talk. So what I kind of wanted to get through was when you're designing programming languages, there are lots of moving parts. We had to describe not just the syntax for our language, we have to describe our abstract machine, what's happening in our abstract machine, we have to describe types, we have to describe types for all our operations and basic constructs, we had to show type safety by, again, going through the steps, describing a type system for our entire machine, and then so on and so forth. So there are lots of moving parts, but the message I wanted to get across was we can take a disciplined approach to all of this. There are steps to take. We have figured it out over decades of research, but we've figured out pretty much what the steps we need to take to describe the language. So here are the steps for specifying a language. You describe your basic constructs, operations, and your compositional operations, and some notion of answer. You describe types for your basic constructs, rules for giving types to basic operations and compositional operations. And then to show type safety, you have to expand it to your entire abstract machine and show this progress and preservation levels. That's it.